Hi everyone. Sorry I can't be there in person, and I'm actually not in my own natural habitat, so hopefully not too many technical things will go wrong. All right, so I heard you guys are interested in mathematics meets AI and sort of the modern version of all of that. I guess that I've been involved in trying to compute things symbolically for a long time, and kind of my goal with Wolfram language has been to kind of have a symbolic representation of kind of everything in the world. So, for example, I don't know, I could say, I might need to make this bigger. I could say something like, that's not good. I could say something like, Portugal, and that's an entity that we can understand. And if I might say something like, what's the population of Portugal? Or I could start computing things about, okay, we could compute, I don't know, what could we say, something about bordering countries, or we could say, let's do this. Let's make a, let's say something like capital cities in Europe. And then we can get kind of a symbolic representation of that. And we could say something like, find the shortest tour among those cities, and we should be able to compute. That's the ordering of those cities, and we might say make a geolist plot of, let's see, what was that? That was line 27 there, of that sequence of cities, and make a plot of how we would visit. Oh, whoops, I should have told it to do that with a line so we can actually see what order it's having those things go in. But so kind of the goal for Wolfram language has always been to kind of make a symbolic representation of anything in the world, whether it's mathematical or not. Now, for example, one thing we might do, let's say we have some axiomatic theory. Let's say something which I invented 25 years ago. The single axiom for Boolean algebra that I found 25 years and about 2 weeks, no, about a week ago. So let's say, for example, we want to say find equational proof of, let's say we want to find the proof that P dot, so the dot here represents, we can think of as representing NAND. So we say P dot Q equals Q dot P, prove that with this axiom. So we can stick that axiom in there, and let's see what it does. And it'll probably grind away for a little while. And then eventually it should produce a proof. And for example, if we can say of that, let me say, I think it's called token event proof graph, correctly. Oh, what a mess. Okay, this is producing a graph that represents the relationship of the lemmas in that proof. Maybe I could say something like, I would suspect I could say vertex labels to none, and then I could make that line 32, great. Maybe that will be an easier to read. Oh, no. Okay, well, here, let me do this. Let me just use a proof graph here. And what I'll be representing here is the kind of relationship between the lemmas that were used in this particular proof. So this is kind of this is something using kind of traditional theorem proving. It's kind of a capability we've had in Wolfram language for more than 20 years. And it's sort of interesting to compare sort of the computational process that's involved in doing this with the kind of computational process that is involved in working with kind of modern neural nets and so on. So let's do something neural netty here. This is our notebook assistant. I could do something really dangerous. I could say something like prove, you know what, I need to have it not be able to see what I just did. Otherwise it will cheat because it can see what I just did. Let me just see. Let me try doing that and see whether, yes, it's now looking at that. So let's say something like prove the commutativity of NAND from, I don't know, from axioms for Boolean algebra. I don't know what it's going to do, but this is sort of an interesting way of seeing kind of the relationship between what you can do with kind of modern LLMs. Let's see what it does. I have no idea what it's going to do. There's one feature. Okay. That's cool. Okay. Here's how you can set up the proof. All right. That's not very impressive. Oh, no, there we go. Okay. All right. So I don't know why it's writing it out so slowly. Okay. Well, it pretty much just did what I just, it pretty much just did the same thing that I did, although I don't think it cheated. So it kind of knows how to go from this kind of linguistic representation to this precise form. And this is kind of a big story. I mean, we built, a couple of months after ChatGPT came out, we had already built kind of a connection between ChatGPT, working with the OpenAI folk, connection between ChatGPT and Wolfram language and Wolfram Alpha. Wolfram Alpha conveniently takes natural language input, and LLMs conveniently sort of work with natural language. So that was easy to connect. Over the last year and a half, we built kind of all of the plumbing to make this much more reliable, so that you can really expect to, talk informally to the LLM and then have it generate kind of solid computational symbolic code that you can then use and make use of. So I'm sure if I just copy this by say insert and evaluate, it'll do this. And hopefully it got it right here. Let's see whether it actually, yeah, there we go. Did the same thing. Let's talk a little bit about kind of the comparison. I guess the multiple things to talk about. One thing is sort of the comparison between what's happening in computation and what's happening in something like an LLM. One of the things that I did recently, well, maybe two things I can talk about. One of them is kind of the comparison between what's happening in machine learning and what's happening in computation. So one question about machine learning is, why does it work? I mean, even approximately, why, what is going on in machine learning? And then another question is, well, is it going to be the case that, for example, something like this theorem proving problem, that I can just eventually ask an LLM to do it, and instead of generating this complicated proof? So let me show you something about the proof. The proof is really quite complicated. I mean, so let me just show you, if I get the proof, instead of getting the proof graph here, let me just go ahead and get a proof data set. And that would be a sort of a computable version of the proof. So here it is. And it has many, I think this particular one has about 100 steps. And you can see it's having all these lemmas. If I go over here, you can see there are steps in each lemma and so on. It's a pretty complicated thing. And so one question is, this proof, it's a complicated proof. Can one sort of understand this proof? This is a proof that, what is this accessible to humans? Is it accessible to LLMs? Let's talk about the is it accessible to humans question. I mean, I was looking at this just recently. I wrote a whole thing about this, of looking at, so for example, if I just write out, this is very small print, this is the full proof from this simple axiom for Boolean algebra. So I mean, just to say what this is, there, I had that at the beginning of this piece. This is the simplest axiom from which you can construct Boolean algebra. And I found this in the year 2000, and I think it's actually the only example still of a sort of interesting and unexpected mathematical result that was kind of found by automated theorem proving. I mean, I found this by enumerating. First of all, I had to have the idea that it might be possible to find this. I then just started enumerating possible axioms for Boolean algebra and using model type methods to prune them out, and then got to a set of candidates which were sort of potential axioms for Boolean algebra, and then proved that this one actually is an axiom for Boolean algebra using automated theorem proving. So now the question is, okay, you've proved that result. It was an unexpected result. It was an interesting result. Can you understand why it's true? And so you could, for example, look at, I was showing you there, I think this is the proof graph, the full proof graph that goes from that axiom to known axioms for Boolean algebra. Before I was just showing you the proof of commutativity of NAND, but this is showing a full set of axioms for NAND, which is what you need to prove completely that this is an axiom for Boolean algebra. So it's a complicated thing. You've got all of these lemmas showing up that are already very complicated in this proof. I was curious recently, is it possible to understand this proof? You're looking at, well, what are the popular lemmas? How big are the lemmas that you get as you go through the steps in the proof? I would say that the main result is that it really is very hard to understand this proof. I mean, a number of people have tried over the last 25 years, but you can kind of start unrolling the proof. You can kind of make the proof, make the lemmas in the proof, work them out just in terms of the axioms and so on. You can start working out, this is the just purely working, if you're trying to prove P NAND Q equals Q NAND P, you can do that by just applying the axiom step by step in judiciously applying the axiom. Well, it turns out that to do that, at least with the theorem proving that we have, it takes about 83,000 steps, and you generate intermediate expressions of about 250,000 terms in the middle. Anyway, I did quite an analysis of whether one can do things like shorten the proof. One thing one can do to try and understand how long the proof has to be is you can kind of make an entailment graph, an entailment cone. You start from the axiom, you just say, what are all the lemmas that you can prove from that axiom? And you start building up this kind of structure in mathematical space, so to speak. This is the kind of structure of all true theorems, all theorems derivable from that axiom in mathematical space. And you then can identify, well, for example, if you're interested in sort of human mathematics, you can ask questions like, well, where are the theorems that we might care about out of the very large number of theorems that we can in principle generate? This is showing where are the theorems that the automated theorem prover picks as being ones that it's going to use as intermediate lemmas. I think there's a bigger picture showing kind of what, but this allows one to know, to be able to compare sort of what are shortest proofs with what are the proofs generated by the automated theorem prover. In the end, the automated theorem prover doesn't do badly. Sorry, that's a different irrelevant piece. The automated theorem prover doesn't do badly in finding the minimal path. By the way, you might ask what happens with other automated theorem provers. Pretty much they're all more or less the same in terms of what they can do with this proof. Okay, so that's a case where, so far as we can tell, there is the proof that you have to prove this axiom is Boolean algebra. It's a difficult proof. How do we think about that? How do we think about the fact that it is so difficult to prove something like that? It's sort of a corollary to Gödel's theorem that there will be proofs of arbitrary length and so on. But the way I like to think about it in terms of a phenomenon I call computational irreducibility, which is sort of a more directly visible issue, and we'll talk about how that relates to what LLMs and AIs, neural nets can do and how they work inside. So maybe I should say something about computational irreducibility. One of the things that's sort of been a story of science for a long time is this idea that science is about predicting what will happen. Well, the issue is, let's say you have some simple computational rule, my favorite kind, that are easy to visualize, something like a cellular automaton where you just have a line of cells, each one is either black or white, and you kind of go down the page applying these rules. Let's say we do that with this, let's say we do something like this. Just started off from one black cell at the beginning, go for like 40 steps. Okay, we have a very simple rule. It does something very simple. It's very easy for us to predict what will happen a million steps from now with this particular rule. Okay, we try a different rule. Let's say we try a rule like this. That's what happens. You can run that a bit longer. It makes a nice nested pattern. It's pretty intricate, but it's still not hard to predict what it's going to be like a million steps from now. So then the thing to do, something I did back in horribly long time ago, 1980s, is to kind of just do the computer experiment of saying, well, if you just look at these very simple rules, you look at all the ones you can make, what do they do? Okay, so here's a collection of those rules. Each one of these is using a different choice of what the outputs are from this particular setup. And many of them you can see do very simple things. But then as you go through here, kind of looking out into the computational universe, the big surprise is, well, this is kind of the first big surprise. It's rule 30 and in this enumeration. And you start it from this very simple initial condition, and it doesn't do something very simple. So let's take a look at that in more detail. This is rule 30 here, and this is what it does. And what you see is that even though the rule is very simple, the behavior you get is very complicated. there's some sort of regularity over on the left. But for example, if you look at the center column of cells here, for all practical purposes, they look completely random. So it's kind of a surprise from one's intuition that something, a rule that simple, can produce behavior that complicated. I spent lots of effort trying to understand how that relates to how nature makes complicated things, and there's lots to say about that, but let me not talk about that here. The main thing here is to ask the question, okay, so let's say I've got rule 30 and I want to predict what it's going to do a billion steps from now. How can I do that? And the main point is that what rule 30 is doing is computationally irreducible. There really isn't a way, it seems, we haven't proved that for rule 30, we can prove that for some other cases, but it seems to be the case that there really isn't a way to kind of jump ahead and figure out what rule 30 is going to do, let's say 1 trillion steps from now, by any procedure that's much more efficient than just basically running it for 1 trillion steps and seeing what happens. So that's kind of an important concept in understanding how computation relates to the natural world, how computation relates to other kinds of things, is this question of so is the computation really irreducible? Is it computation you sort of have to do, or is it something where you can do clever math, for example, to get sort of an exact solution and just jump ahead without having to go through the steps? And one of the big results of a lot of science that I've done is that computational irreducibility seems to be really common and really important in a lot of different situations, whether you're thinking about, AI ethics and can you predict what the AIs are going to do, whether you're thinking about physics and trying to understand origins of things in fundamental physics, and so on. It's very directly related to things like the second law of thermodynamics and so on. Okay, so how does that relate to sort of questions about AI? Well, one question is, can the AI beat computational irreducibility? Is it the case that somehow it can figure out how to jump ahead, and even though we don't think we have, that somehow the things we think we've shown about computational irreducibility can be avoided by AIs? And so let me show you some examples of what actually happens if you try to do that. Actually, it's worth getting a sense of what AIs can, what neural nets can do and can't do. So there's a typical simple neural net. There's what it does. There's some weights that it might have. This is a neural net where you're just feeding in a value x at the top. You're getting f of x out at the bottom. And even doing something very simple, like you train the neural net to work out that sine wave, you've got a bunch of values trained over on the left there. And then you ask the neural net to extrapolate, to generalize. It does a fairly crummy job. And for example, this is what happens in successive steps of training, successive thousands of steps of training of the neural net. It doesn't succeed in figuring out that extrapolation. Similarly, if you try different sizes of neural nets, they will have different levels of performance in being able to do that extrapolation. None will succeed in this particular case. So a question you might ask is, well, what happens if you want to, for example, figure out the behavior of one of these cellular automata? Well, you can make a nice little transformer net, and you can try and run the transformer, and here's what you find. What you find is that when, for example, there's repetitive behavior, the transformer can nail it. When the behavior is more complicated, it fails. And so here are some examples of, I think these are successive levels of training, I think, of this. And so the kind of empirical answer is, no, it isn't the case that the neural net somehow can swoop in and jump over computational irreducibility. You're kind of stuck with computational irreducibility. So, you can ask questions about what happens, I don't know, for example, well, even let's take protein folding. So this is, those are some proteins, those are actual crystallographic structures compared to what you get. Let's see, what's a good example? That's from LLM-based folding of protein. I'm happy to say you can now do all this stuff directly in Wolfram language. But in any case, you can kind of, roughly what happens is when the protein has fairly simple behavior that sort of looks like it might be predictable, then the LLM does pretty well. When it looks much more random, the LLM is, qualitatively roughly right, but in detail not really right. Same thing actually happens, sort of interesting, with the three-body problem. So this is just gravitational three-body problem. Use what is this? This is just a simple neural net here and try to predict the three-body problem. And what you find is that when the three bodies are doing simple things, it does quite well. When they're not, it doesn't. So let's talk about kind of what's happening inside. Let's see, inside these neural nets. The question is, so let's say we have a neural net here that's mapping from x to f of x. The function f of x is on the right-hand side. We train that very simple neural net. The weights that are illustrated there with the colors correspond to that particular function f of x. So for example, we feed in different values here, and what will come out of the neural net are the values corresponding to f of x. Okay, so a question is, can we tell what's really going on here? So I got curious whether we can whether we can find a simplified version of these neural nets, which are easier to visualize and easier to kind of analyze what's happening. It doesn't help in standard neural nets that you're using real number values and real number weights, which don't play very well with standard sort of ideas about computation and symbolic kinds of things and so on. And it's worth kind of looking inside the neural net. This is, I guess, the weights, the activations of different neurons inside the neural net. It's pretty complicated what's going on in there. When you look at training of that neural net, there's kind of what you see in the successive weights being trained, and you see a lot of interesting phenomena there. This, I think this is the loss curve for that particular neural net training. Different loss curves for different rolls of the dice, so to speak. And okay, so the question is, what's going on in this neural net? What can we get a more, in a sense, mathematicized understanding of what's happening? So the first thing I was trying to do was to simplify the neural net, because it's just a mess to deal with all these connections from here to there. So I looked at just a grid of neurons instead of a very connected set of neurons. Turns out you can still train a thing that is a grid of neurons to do this very simple task of computing this function f of x. This is what happens in sort of the activations of those neurons at different values of x. Again, complicated things are happening inside, but you can kind of see this is actually what happens. This is what the training looks like. In successive rounds of training, you're successively filling in the weights on this grid to be able to give that result. Okay, so then, let's see, what do I have here? Well, these are loss curves. They look pretty much the same as those things always look. If you change the size of the grid, for smaller grids, you just can't learn that function, but for bigger grids, it works just fine. Okay, so now the question is, what can we simplify this even further? Okay, to explain that, I should say something about another thing I've worked on recently, which is models for biological evolution. And that might not seem relevant, but I think it is. Let me show you that. So the big idea is, let's say we have that little creature over on the right. It starts from one red cell at the top. It uses that genome, those rules on the left. It runs for, I don't know what it is, 60 steps or something, and then it dies out. Okay, so this is our, so now let's imagine doing adaptive evolution on this creature. We're going to successively update its genome by making point mutations in the genome. And we're going to do that, and we're going to continue doing that, but we're going to allow those mutations that cause the thing to not decrease in lifetime, we're going to keep, and the ones where it does decrease in lifetime, we're going to throw away. So this is what happens in one particular roll of the dice. You start off from something, just a null rule, and then these are the successive kind of waypoints of kind of learning to live a long time. And you can kind of see this is the actual sequence of changes in the genome that let it live that long time. If you look at the loss curve, and now I've tipped it the other way up because it's kind of a fitness curve in biological evolution, this is showing as a function of number of steps of the adaptive evolution, every red dot is an attempt, is a possible genome, so to speak. And for many of them, it kind of doesn't, it just stays, it can't get anything new, it can't get anything new. Eventually it has a breakthrough, it figures out a new way to live a long time. And what's interesting here to me is that the kind of the behavior you see is there's all kinds of different ways that one of these systems can learn to live a long time. And you find that this is kind of like seeing the different paths in biological evolution. These models are simple enough. Well, by the way, the way that they live a long time can be very ornate. I mean, let's show you an example. These are ones that live a long time that happen to be symmetrical. They're very ornate things. One thing that's important about them is if we look at ones that live a long time of a particular type, you say, why do these live a long time? Okay, well, there are a few cases here where we might point at it and say, I think I could understand the mechanism for how it's making some kind of counter and living this period of time and so on. But most of these, it's pretty hopeless to say that. It's just, well, it happens to live, whatever that was, 216 steps and then it dies out. It's kind of in-your-face computational irreducibility. There's really no way to have kind of a jump-to-head kind of narrative explanation of what's going on. It's just, this is the lump of irreducible computation that this evolutionary process found. It is successful in living for 200 steps or whatever, but we don't have really a way to say why. It's very similar to what happens with that theorem I was showing you. It's kind of, there is a thing you can produce, but we can't really say why. Okay, so you can study kind of lots of interesting things to study about kind of biological evolution, but let's go back to machine learning. In that case, we can, what is the analogy between what we're seeing in biological evolution and what we see in machine learning? So I tried to make an even simpler model of machine learning, just using, why not, cellular automata. So what I did was to look at, to have, instead of remember I had this grid of neurons, so now I've got this grid of very artificial neurons, which are just, every neuron can have one of two possible states, one of two possible weights effectively. And depending on, for one of those weights, it is running one of these rules, for another weight, it's running the other rule. So now we're asking the question, these are different sort of patterns of weights effectively that show different behavior when we feed in the input of one black cell. Okay, so now we can just run essentially machine learning, or which is kind of the same story as biological evolution. We can again just run a training process where we're saying, just keep on trying to change this collection of weights, this array of bits, change that array of bits so that, for example, in this case, we live exactly 50 steps. Okay, so this is the result of doing that, and these are kind of the waypoints of where it managed to make progress in living longer, and that's the way it solved the problem. By just doing adaptive evolution, this pattern of bits solved the problem of living exactly 50 steps and then dying out. And we see again, this is kind of the loss curve or fitness curve showing us how it learned that, so to speak. Well, now we can roll the dice again and we can say, well, what are some other ways you could learn this? These are other possible ways it learnt how to live 50 steps and then die out. What's interesting about this? Well, the main thing that's interesting is most of the ways it learnt to live 50 steps and then die out are incomprehensible. They're just complicated things where it happens to live 50 steps and then it dies out. A few of them are explainable, but most are not. And so essentially, I mean, the one can go on and do the same type of thing with more elaborate sort of machine learning questions. This is, I think this is, let's see if I have this. This should be learning a function using the same kind of approach. I was learning that same function, that same step function I was looking at before. Is this it? I'm not sure that's it. No, that's activations. Anyway, you can learn that same, is this it? No, that's the training for it. So you see, again, what you're doing when you learn a function, in this case, all you're learning is that bit pattern. And then you can kind of ask, and this is kind of the function you learnt through that bit pattern, and eventually it does a pretty good job of learning that function. So the question, this is, let's see, where are we? Here, well, okay. What's the basic point here? The basic point is, if we want to answer the question, how does machine learning work? What is machine learning actually doing? That's been quite mysterious. why can you learn these things? Why is it the case that when you bash the system hard enough, it will learn some wide class of functions? I think the end result is that what's happening is machine learning at a qualitative level is finding lumps of irreducible computation that happen to fit together in such a way as to do the thing that you were trying to learn to do, so to speak. So it's sort of an analogy. If you think about, I don't know, engineering, you're trying to build a wall. Well, one way you can build a wall is you first manufacture bricks that are nice cuboids, and then you put them together and you make this very well-arranged, well-organized wall. That's kind of the traditional engineering programming type approach. An alternative is you just say, well, I'm going to look at the rocks that are lying around on the ground, and I'm going to figure out how I can stick one rock in place in this place and so on to build up this wall. That's kind of what machine learning is doing. It's getting to the objective you wanted to get to with by using kind of the naturally occurring lumps of irreducible computation that it can find. That's sort of the qualitative picture, I think, that emerges for how machine learning works. That qualitative picture already tells you things like it's not likely to be explainable what's happening inside because it's just, well, it happened to find this particular rock that was a piece of irreducible computation and so on. Well, okay, many different things I could talk about, but let me try and let me just mention a few more things, and then maybe we can turn this over to discussion. I just wanted to mention something about kind of, well, what can these AIs? How do we think about sort of what AIs can think about, so to speak? Maybe we could talk about. Well, I think I already mentioned. Let me look at this for a second. So let's actually talk about math for a second. I was already showing you some theorem proving kinds of things. You can imagine, I mentioned sort of building up math by just going from one theorem to another theorem. You can kind of build up math by taking, let's say, two theorems and combining them to get another theorem. Well, then, for example, proofs then become paths in these kinds of networks. So, for example, there's a proof path, there's the actual symbolic version of that proof. But as I mentioned, you can kind of go and you can start building up sort of all of mathematics in a sense by starting from its axioms and then just building from there. And let's see this. Sorry. Here we go. Okay, so for example, we can take these are okay. Those are using the standard axioms for Boolean algebra with and, or, and not, and this is basically building up the complete entailment cone, one can call it. In physics, it will be a light cone starting from some event. What are the consequences of that event? In metamathematical space, that's an entailment cone of what theorems are entailed by assuming these axioms. So this entailment cone, what's sort of interesting is there are an infinite number of theorems eventually in the whole entailment cone, but occasionally we'll get to a theorem which humans think is interesting. So in other words, in the space of all, in all of metamathematical space, there are all these possible theorems. Only a tiny fraction of them are ones that we humans consider interesting. You can kind of do a little bit of analysis. For example, let's see, let me find one here. You can do a bit of analysis of kind of existing structures in mathematics, like those are the axioms, those are the theorems of Euclid, starting from the axioms that Euclid writes down, and then proving 460 or so theorems that's sort of the proof graph structure for Euclid. For example, this is the proof graph structure. I think this is in either Lean or MetaMath for the Pythagorean theorem from the axioms of set theory. Rather complicated, but you can get, it's sort of interesting to see, where if you kind of lay out metamathematical space, it's interesting to see sort of where the famous theorems of mathematics roughly lie in that approximation to metamathematical space. But I think that there are many things to say about kind of how higher level mathematics of the kind that humans understand emerges from this very low level structure of all of these axiomatic kinds of steps. It actually turns out to be directly analogous to the way that physical space emerges from underlying discrete structures. Different topic. what I wanted to mention, so one of the things to mention here is kind of in metamathematical space, there are pieces that are sort of identified by humans as being theorems we care about, things that are interesting and so on, but there's a vast amount of metamathematical space that we've never explored. Okay, well, so there's an analogous thing you can think about for AIs. You can say, for example, let's say we're using an image generation AI, and we have this image generation AI, and it is, for example, able to, we tell it, make a picture of a cat in a party hat. And it will kind of go around and it will use, stable diffusion or something to go and try and construct something which matches the description of a cat in a party hat. Now the question is, what does that whole space of possible images that the AI can think about, what does it look like? Well, here we're moving away from, in the embedding space, basically, in the feature space of possible images, we have the cat in the party hat at the center, and we're kind of moving away from the cat as we go around here. This is I don't know, a 600-dimensional space or something. So we're just seeing one slice. This is one slice of what we might call Cat Island. So what's interesting here is we have a human description of the cat in the middle there. As we go to other kinds of things, these are other projections of Cat Island. As we go to sort of other places in this generative AI space, we get things which we humans right now don't really have good descriptions of. We can see the structure there, but we don't have a good word that describes that structure. And so what's sort of interesting to see, okay, there's a structure where we can sort of roughly see, maybe have a word for it, but there are many where we cannot. And so it's sort of interesting to see in this full sort of space of what an AI can think about, so to speak, based on the training that it's had. We can ask the question, sort of what fraction of that space is covered by concepts that we have names for, like the 50,000 words in English or something. The answer is, well, even in this particular very simple case, it's about 1 part in 10 to the 600. So only 1 part in 10 to the 600 of what one might call interconcept space, analogous to sort of interstellar space. There's, our concepts only cover a microscopic fraction of all of interconcept space. Well, there's much to say about kind of what is interconcept space, and what is the kind of, both in the metamathematical case, which is much sort of more precisely defined, and this kind of generative AI space, what is that whole object that is kind of the full thing that we are exploring pieces of? It's something that's emerged from things that I've done in fundamental physics in the last few years. We made sort of this breakthrough about 5 years ago in understanding kind of the machine code of physics. And I mean, this is a long story. I'm happy to talk about it if people are interested, but maybe not on demand. I'm happy to talk about it. But the bottom line there is sort of underneath this model of physics is this thing that we call the Roolead. And the Roolead is kind of an interesting object that one could have studied a long time ago, but none of us thought to do it. Which is, it is the entangled limit of all possible computations. So for instance, this is, there's a rule for a Turing machine, there's the Turing machine running. This might be a rule for a multi-way Turing machine, a Turing machine that's not deterministic, it has multiple paths of possible computation. And we can ask the question, well, if you just run all possible Turing machines, starting off from all possible initial states, this is sort of the beginning of the structure that you get by running all possible Turing machines from all possible initial states. And in general, what is the structure that you get by running all possible computations from all possible initial states and so on? And you get this very complicated kind of entangled object. It's entangled because two different computations may end up producing the same state, and you merge those states, and that produces this kind of entanglement of the structure. Anyway, the object that you get is a sort of unique object that is kind of a representation of all possible computation. We call it the Roolead, and I'll leave sort of the cliffhanger statement that one of the things I've been most excited about the last few years is the fact that it seems that once you start with this Roolead object, if you want to know why are the laws of physics the way they are, the sort of key laws of 20th century physics, things like relativity, quantum mechanics, the second law of thermodynamics, why do those things work the way they do, it turns out that, to my great surprise, it's possible to derive those laws of physics, not just say the universe happens to be this way, but say, given the Roolead, and given one more thing, which is given what kind of observers we are of the Roolead, what slice of this set of all possible computations we actually sample. It takes only some very weak assumptions about the way we are as observers to be able to derive from the structure the actual precise laws of physics that we learned in the 20th century, which is quite exciting as far as I'm concerned. I mean, just to say the things that we have to assume about ourselves are that we are computationally bounded observers. We are observers who can't sort of break computational irreducibility. That's one thing we have to assume. The only other assumption we have to make is that we believe we are persistent in time. Even though we might be made of different atoms of space at every successive moment, we still believe in our single thread of experience through time. And that's kind of how we view the universe, is we assume that we are persistent in time. Anyway, I should, talking of time, I've probably gone on too long here, but I'm happy to have whatever discussion, questions, comments you'd like. Please, I see. Well, I can't hear anything, so if just, oh, great.
Hello, Stephen.
Hi.
I have a question. You say that you think the neural networks are finding like building blocks of irreducibility, right? But you are using very special kind of neural network, using your favorite failure automata. Okay, so how does it apply to, let's say, a regular deep multi-layer perceptron? This irreducibility means that there are some steps that should be taken, or that. So how that? And then I ask you, if this is the case, you can learn everything with a single layer. So maybe it's very difficult to learn, but it still is possible to compute it. So how would that relate with computing in steps? Or so?
Okay, so I mean, this question of how do you kind of get a qualitative view of what's happening inside, let's say, a multi-layer perceptron? It's just technically difficult, because you've got a bunch of real numbers, you've got all these connections. You know, one very simple question, actually somebody at our most recent summer school was studying, was you just put in weights at random. What is the, you know, this is a very minimal question. You put in the weights at random, what functions, what is the measure on the space of functions that the neural net represents? We don't even know the answer to that. And it's already a quite complicated question. I think the issue is, again, because we don't have a good way, with integers, we understand computation theory at some level. With real numbers, we just don't have a robust way to talk about computation theory. We never have had. And I think the, so, you know, that's why it's just technically difficult. My feeling is, let me give you an example. Okay, so, you know, you might ask sort of what's the comparison between things that are discrete, things that are continuous. So I'll show you an example. Let me pull something up here. Let's see. So, you know, you've seen all these cellular automata and things, but, you know, what happens in systems based on numbers? Okay, let's take a look at, for example, PDEs. So there are, there are some sort of typical PDEs, you know, diffusion equation, wave equation, sine-Gordon equation, okay? They look very simple. So I was curious many years ago, 30 years ago now, I was curious, if you just start searching the space of possible PDEs, what do you find? Well, it turns out you very quickly end up finding creatures like this. This is a very simple nonlinear wave equation. It starts off from a Gaussian initial condition, and it makes a big complicated mess. So now the question is, well, you know, what can you say? The first point is, this is kind of the same type of thing that you see happening in Rule 30, except it's now with real numbers, it's a PDE, et cetera, et cetera, et cetera. So you say, well, you know, does it help me that it's a PDE in analyzing it? No, it makes a horrible, complicated technical mess. And for example, this particular PDE, I mean, we've used it as a test for our differential equation solving capabilities in Wolfram language for the last 30 years or so. But the fact is, if you say, did I really get it right? After some number of, some amount of time here, is the solution actually correct? We actually have no idea. We can say, well, our numerical scheme looks like it's converging, but we can't prove it. We can't really prove anything about it. But my main point here in showing this is phenomena that we see in these discrete systems, they seem to show up just fine in these continuous systems, but it's much harder to get one's arms around the case in continuous systems. So I fully expect that any phenomenon you can see in these discrete approximations to neural nets, you will see in continuous neural nets as well. It's just technically much more difficult. I mean, I would love to, now I'll make another comment, which is that after I did this work on this fully discretizing neural nets, there's sort of been an effort started. A number of obvious companies have gotten interested in, can we actually implement this as a practical scheme for doing machine learning? Because if we can, we don't need all these floating point units. And we can cut out a huge amount of stuff on GPUs and things like this. And so, that's just starting. But I have to say, my assumption is that it's going to work just fine. My assumption is that that machine learning is robust enough that it doesn't matter whether you have continuous weights. I mean, you might have thought, oh, we have continuous weights because we need to do small scale changes and we need to do back propagation and so on. If you have, it's like saying, well, you've got all these bits and you can package these bits up into real numbers and you can tweak the bits in the real numbers, or you can just say, I've got a big bag of bits and I'm going to adjust individual bits in this big bag of bits without sort of hierarchicalizing the bits into the high order and low order digits of a real number. So I think anyway, my guess is that it's going to work just fine to do machine learning just with bits rather than with real numbers. I mean, we saw the same kind of thing in the mid-80s. I invented this method for doing fluid dynamics with underlying bits that represent idealized molecules. And so you have kind of a choice. You can either start from the fluid equations and discretize them to put them on a computer, or you can work upwards from these discrete molecules and try and get enough of those discrete molecules to approximate the continuum. Turns out it works just fine to start from the discrete molecules and work upwards, so to speak. I think the same thing is going to be true of machine learning. I think that the mathematics, it might be the case that there's some clever thing you can do to sort of jump ahead by using sort of real number mathematics. I mean, it's always a cautionary tale to realize that, the questions about polynomial equations and so on are decidable over the reals and are not decidable over the integers. So it's kind of, there's something you get by having that structure of real numbers. But, my guess would be, I think it's going to be pretty hard to do traditional math on neural nets. I think you're going to run, right into computational irreducibility, which is kind of a place where the traditional, where you have things like that theorem that I was showing you earlier, where, you have this automated process, but there isn't really a way to do what one might call higher level mathematics. I might say, I mean, just as a comment, the possibility of doing higher level mathematics is interesting. In other words, I showed you that picture of the Pythagorean theorem derived from set theory in some proof assistant system. It's really complicated. It's, I think, 7,000 lemmas. So the question is, why is it possible to talk about mathematics just in terms of the Pythagorean theorem without having to dive down and say, oh, by the way, I'm defining a real number this way, and et cetera, et cetera, et cetera. Why is it possible to do higher level mathematics? It's not obvious that it would be. It's not obvious that you wouldn't always have to be kind of looking over your shoulder, worrying about the definition of real numbers and things when you do simple geometry. The fact that you don't have to do that is deeply connected to the fact that things like fluid dynamics are possible, the fact that you can talk about this collection of a large number of molecules just in terms of fluid velocity fields, rather than having to dive down to the individual molecules and so on. It's also deeply related to the derivation of these laws of physics and so on. But it's basically the fact that higher level mathematics is possible is a non-trivial statement about how we observe the mathematical universe. Sorry, a bit philosophical, but perhaps interesting. Other questions, comments, whatever. I see a hand up there.
Thanks for the fascinating talk. My question is, do you think there are distinguished regions or points in the metamathematical space or theorem space, if you like? If so, do you expect an underlying geometric organization of mathematical theorems as we see in theoretical physics?
That is a fascinating question. Okay, so the one question is, how homogeneous is metamathematical space? And, you know, in physical space, the physical universe is fairly homogeneous at some level. And certainly the laws of physics you can translate from one place to another. So what is it like? You know, in physical space, we're sitting on this planet, we could be sitting on another planet. We would have sort of the same laws of physics, but a different night sky on another planet. The question is, what's the analog of that in metamathematical space? And I think the answer is that as you move around in metamathematical space, you're translating from one way of defining mathematics to another. So for example, you might be translating from algebra to geometry or whatever. And what we're saying, if it is true, that, as I think it is, that metamathematical space is fundamentally quite homogeneous, it means that there is a translation from any one field of mathematics to any other. And that kind of tells one, I mean, one of the discoveries of modern mathematics has been all these sort of miraculous dualities between different fields of mathematics. Kind of the thought here would be that is a reflection of the homogeneity of metamathematical space. Now, you might ask, are there distinguished points in metamathematical space? For example, dotted around metamathematical space will be theorems that we've given names to and so on. We can talk about, you know, which sort of how we determine where we colonize in metamathematical space. But one comment to make is about overall homogeneity. So in the physical universe, space is kind of fairly homogeneous, but it does have singularities in it, black holes. And so, for example, a typical Schwarzschild, non-rotating black hole, at the center of that black hole is a space-like singularity. And what is that? It's a place where basically time ends. In traditional general relativity, it's a place where every geodesic has finite length, that in finite time, it hits that singularity, the geodesic ends. In our models of physics, which I didn't really talk about, the rewrite rules that are the progress of time, basically, those rewrite rules just don't apply at the center of the black hole. At the center of the black hole, you have basically terminated your rewrite process and time has stopped. So black holes, in the simplest case at least, black holes are places where in the universe where time stops. Okay, so what is the analog of that in metamathematical space? I think the analog is decidable theories. So in a sense, what you might think as you kind of tool around the universe, you can go along these infinite geodesics, you can kind of move around infinitely. Similarly, in undecidable theories in mathematics, there are proofs of arbitrarily great length. In decidable theories, there's sort of a bound on the lengths of these proofs. And I think that the analog of a black hole in physical space is a decidable theory in metamathematical space. So it's this kind of bizarre, and it turns out that the Einstein equations in physical space, which tell you that when you have lots of energy density, you will curve space. The analog of that in metamathematics, I think, is that when you have a lot of proof density is the analog of energy density. And I think that what happens is that when you have a lot of proof density, you inevitably, just like in physical space, you inevitably generate a black hole when you have enough energy mass energy density. So similarly, when you have enough proof density in metamathematical space, you generate the metamathematical analog, namely a decidable theory. And so there's this sort of bizarre thought that the future of the physical universe of a bunch of black holes being formed is similar to the future of the metamathematical universe of a bunch of things that sort of collapse into decidable theories. That's a thought, at least. My guess is, as I say, my current belief is that there is basically a lot of homogeneity in mathematical space. The question of where are the theorems that we have given names to, for example, that's an interesting question. I've looked at that for Boolean algebra, and there is a actually quite principled way to figure out which theorems we give names to in Boolean algebra, which is basically you just order all theorems of Boolean algebra in lexicographic order, and the ones we've given names to are more or less the ones that can't be proved from anything earlier in the list. They're ones that sort of give you, are the simplest statements of new information. But I don't have a general way of knowing, sort of where are the places we give names to the theorems that are out there in mathematical space. I had hoped that maybe LLMs could help me with this. So I thought the LLM reads the mathematical literature. There are 4 million theorems in the mathematical literature. It's like, okay, LLM, where out of the space of all possible theorems, where are there ones that, based on the preferences of humans as displayed in those 4 million theorems that are out there in the mathematics literature, show me other ones that are kind of like those. I thought that might work. So far, my experiments doing that have been pretty hopeless. I mean, I think the problem is that as soon as you have a theorem that's not really close, it's like this interconcept space idea. As soon as you have a picture that isn't really close to being a picture of a cat, it's hard to tell what the heck it's a picture of. And maybe it's just, as soon as it gets, I don't know. So far, that has not been a successful experiment. I have hopes that it might be successful and that you might be able to, I mean, my general view of the sort of our expansion in mathematical space is that we have to go step by step. If you jump to a random place in mathematical space, you will get an incomprehensible theorem. It's similar to kind of jumping to a random place in the space of all possible computational rules. You get something where you can see the behavior, but you can't understand it. So my feeling is that the human progress of mathematics has to be in these kind of modest steps, building on things we already have and sort of building up our understanding. It's kind of similar, I think, to what happens in linguistics and language. We can, we're building from things we already know. We invent a new word that comes from combining, a phrase into a single word and so on. We're kind of progressively building up something where we can have both for an individual and collectively, we can have a way to describe things that sort of we can communicate with. That was a very interesting question. Okay, more, please.
Thank you for the talk. The idea of computational irreducibility seems very important, and I seem to have understood that you claimed that there were examples for certain rules of the cellular automata that indeed were computationally irreducible. If I understood that correctly, can you sort of walk me through how one could prove such a statement?
Yeah, right. So the thing that underlies computational irreducibility is another concept that I think is also very important, which is a thing I call the principle of computational equivalence. And what that says is that above some very low threshold, most systems that you can construct are equivalent in the sophistication of computations they can do. So this is kind of a bigger, tighter version of the existence of universal computation. The fact that there exist universal computers is, you might say, well, there exist universal computers. We've known that since the 1930s. The question is, one question is how ubiquitous is universal computation? And then universal computers, well, let's start off with that question. So one of the surprises has been that actually so the principle of computational equivalence basically says, as soon as you can't obviously compress what's going on, it's likely to be as sophisticated as it could be. In particular, it's likely to be computation universal. Okay, so I'll show you an example. Let's see. Let me show you. Okay, so one example, this is another rule of this type. This is rule 110. It happens to grow only on the left-hand side. This rule, let's look at it for random initial conditions. Oops. Okay, so there it is from random initial conditions, and you see it has these little structures. And so the question is, can you use those structures to build?
Sorry to interrupt. We can't see the screen.
Up. That is a problem. Excuse me. That's because I incompetently failed to share. Okay, can you see that now? That you're seeing the right screen? You're seeing yes. See this rule 110 thing? Did I share the right screen?
We see a bunch of pictures and list of
Okay, okay, that's not the right screen. Sorry, guys. Okay, that should be right. Okay, so just check the right thing. Yeah, okay. Okay, so this is just another one of these rules. It happens to be rule 110. I had showed you before. This is it, starting from random initial conditions. And what you see is there are a bunch of these little structures. And the question is, it looks vaguely plausible that you can assemble those structures to correspond to a Turing machine and so on. And it turns out, yes, you can. You can show that rule 110 is computation universal. Well, so that puts one on sort of a hunt for, is it really true that the simplest instances of things that aren't obviously trivial turn out to be computation universal? So another case I looked at years ago is Turing machines. And so this is the simplest Turing machine the simplest rule for a Turing machine that is not obviously simple in its behavior. And turns out, yes, young chap, wasn't quite as young anymore, proved that, yes, indeed, this particular Turing machine, the simplest Turing machine that isn't obviously not universal, is universal. So these are sort of these are circumstantial pieces of evidence for this principle of computational equivalence. Okay, how does the principle of computational equivalence relate to computational irreducibility? Well, let's say you've got one of these systems, like Rule 30 or something. The question is, how do you jump ahead of this to predict what's going to happen? Well, at some level, you as the predictor have to be computationally more sophisticated than the system itself. And what the principle of computational equivalence is telling one is that won't be the case. That as soon as you have a system like this that isn't obviously simple, it will be as sophisticated as anything can be. And that means you won't be able to jump ahead. So one sign of that is this system, even though it's really simple, even though it has really simple rules, will be computation universal. Now, there are many footnotes to this whole thing, many of which have not been, are very difficult to nail down. But so, for example, one of them is this behavior is complicated even with a simple initial condition. When you look at Rule 110 being made to emulate a Turing machine, the initial conditions are very complicated. The fact that it still does something complicated even when the initial conditions are simple, that's a non-trivial fact, which we don't have such great mathematical tools for understanding. The other thing is sort of nailing down what it means in terms of, for example, computational complexity theory, what it means to say that you kind of can't jump ahead. There have been all sorts of efforts to do that. I have to say, some of them, people sort of have ended up setting up rather straw versions of what one means by computational irreducibility, and the results aren't so interesting. For me, computational irreducibility has become almost an axiomatic concept because it's something, well, the principle of computational equivalence is sort of an interesting kind of thing. It's sort of a bit like, well, it's, at some level it is definitional, at some level it is provable, at some level it's kind of a fact about the universe. It has a complicated status, rather similar actually to the second law of thermodynamics. That is at some level sort of a definition of heat, at some level a provable statement, at some level a fact about the world. This is a similar kind of thing. So that's its kind of it's a philosophically slightly complicated thing. But the intuition is, as I say, what we can nail down is things like, yes, the simplest system of this type turns out to be computation universal. That's the type of thing we can nail down, which gives us kind of is triangulating on this more general concept of principle of computational equivalence and its consequence. Once you have the principle of computational equivalence, you pretty much have to have computational irreducibility. So that's I mean, it would be, I have to say, sort of the further formula, okay, here's an interesting thing. I suspect that the things I've done, for example, in fundamental physics, that I've done based on explicit models of, hypergraph rewriting and all this kind of thing. And then taking limits of that and trying to understand how that works. I suspect that much like sort of the derivation of special relativity from things like the speed of light is constant in all frames, etc., that there is a similar way of deriving much of what I've been able to figure out about physics simply from essentially the philosophical assumption the principle of computational equivalence is true. And that becomes sort of a foundational claim about not just physics, but other things. So I don't know, this is a complicated area, and I don't, but that's kind of, I think, something about what we know so far.
Thank you very much, Stephen. That was very enlightening.
My pleasure. Well, look forward to meeting you all sometime, someplace.
Yep.
But good stuff. Thanks. Bye.